All right, let's get right into it. Welcome to The Explainer. Today, we're taking the magic of generative AI, that abstract cloud-based stuff, and grounding it into something very, very real. We spend so much time obsessing over algorithms and parameters that we completely overlook the massive physical infrastructure making it all happen. So today, we're tracking the physical life cycle of a microchip. We're going to follow it from the raw, actual dirt it's mined from, all the way to its final resting place in a recycling bin. It's a fascinating and honestly sometimes shocking cradle-to-grave story.
Now, to really grasp the stakes here, we have to look at this absolutely staggering juxtaposition. On one hand, you have companies like NVIDIA pulling off a massive 1,000-fold increase in AI compute power in just 8 years. But that incredible leap, it's anchored to a pretty grim physical reality. Extracting just one single ton of the rare earth elements needed to build this hardware produces 2,000 tons of toxic waste. 2,000 tons!
Here is our roadmap for today. First, the AI hardware boom. Second, the rare earth reality. Third, extending the GPU lifespan. Fourth, taming the e-waste tsunami. And finally, towards a circular future. Section 1. The AI hardware boom. Efficiency versus scale.
We are right in the middle of this intense race between energy efficiency and massive computational scale. NVIDIA's recent sustainability report paints a really interesting picture here. They're heavily leaning into accelerated computing, which basically means using specialized GPUs to do a bunch of tasks all at once rather than one by one. This lets massive AI workloads run way more sustainably than they ever could on old-school CPUs. They're even using this horsepower to run things like Earth 2. It's literally a digital twin of our planet that can predict weather 3,000 times more efficiently than traditional physics models.
And the sheer scale of innovation, it's just wild. We've gone from 19 teraflops on the Pascal chip to a mind-bending 20,000 teraflops with the new Blackwell architecture. That is a 1,000x increase in AI compute in just 8 years. But the crucial part is that Blackwell also gets a 20x energy efficiency leap over CPUs for certain AI workloads. This efficiency is exactly what's allowing AI to actually help us discover things like new battery materials that use 70% less lithium.
Section 2. The rare earth reality, mining the magic.
Okay, so if we take these pristine, beautiful pieces of technology and trace them backward, we find out pretty quickly they don't just magically appear. They completely rely on extracting rare earth elements, or REEs, from the ground. And there is a huge, stark contrast between the clean, high-tech promise of the cloud and the dirty reality of global supply chains. Because of lax environmental regulations in dominant mining regions, especially in China, which has historically controlled up to 85% of the market, we're looking at massive environmental hazards. Just take the Bayan-Obo mine, the largest rare earth mine in the world. It has this unlined tailing pond holding over 70,000 tons of radioactive thorium. And that thorium is actively seeping into the groundwater, moving toward the Yellow River at a rate of 20 to 30 meters every single year. The sheer physical scale of this just kind of hits you when you break down the math. To extract these elements, you're pumping toxic chemicals into the earth, or using these giant leaching ponds. For every single ton of rare earth produced, the process kicks out 13 kilograms of dust, up to 12,000 cubic meters of waste gas, 75 cubic meters of wastewater, and a full ton of radioactive residue. That is a heavy, heavy toll on local communities and their water supplies, all just to build the foundation of our digital future.
Section 3. Extending the GPU lifespan, the secondary market.
So, knowing that massive environmental cost, what exactly happens when hyperscalers like Google or Amazon are done with these chips? Well, they don't just vanish into thin air. They actually enter a really thriving, highly structured secondary market. There's this common myth out there that a GPU is economically dead after 2 years because tech moves so fast. But look at this timeline. We call it the GPU value cascade. For the first 2 years, sure, a chip is running cutting-edge frontier model training. But in years 3 and 4, it shifts to real-time inference. And then in years 5, 6, and even beyond, it handles batch inference and analytics. So older hardware actually retains massive economic value for 5 to 7 years, sometimes longer, just by shifting to less intense workloads. The pure economics driving this cascade are super interesting. Back during peak scarcity, a brand new H100 GPU was trading for up to $50,000 on the secondary market. No joke, 50 grand. Now compare that against a refurbished older generation A100 GPU, which you could grab for around $7,800.
If you're a neo-cloud operator or an enterprise business, your main metric isn't having the shiniest new chip. It's the cost per completed task. And for a huge chunk of inference workloads, paying a fraction of the price for a used A100 is just a much smarter, highly economical business move.
Section 4. Taming the e-waste tsunami. AI's end of life.
But look, no piece of hardware lives forever. Eventually, every server hits the end of the line, which brings us face to face with a massive, impending challenge: AI e-waste. Right now, we're seeing trillion-dollar investments pouring into AI infrastructure. And guess what? Every single piece of that hardware will eventually become e-waste. Because of this, the global IT asset disposition market, or ITAD for short, is projected to roughly double to $54.5 billion by 2030. We are staring down the barrel of a hardware churn explosion. And the really scary part is that legacy recycling programs, the ones still running on manual spreadsheets and paper certificates, they just cannot handle this kind of volume securely or sustainably.
To safely dispose of these super-sensitive, highly valuable assets, the whole industry is being forced to modernize. We're talking a total shift to automated item-level processing. This means scanning barcodes and RFID tags the absolute second a piece of hardware arrives, orchestrating the entire workflow automatically, generating digital proofs of data erasure, and tracking logistics in real time. It is all about knowing exactly where a specific data-bearing drive is at every single millisecond of its end-of-life journey.
And here is where we hit the ultimate irony of our story. We are actually starting to use AI to solve the AI waste problem. Next-generation IT/AD providers are using machine learning models to instantly figure out the absolute best outcome for every single component. The AI looks at device age, condition, and current market prices to decide on the spot whether to reuse, redeploy, resell, donate, or recycle the part. This maximizes the financial return while keeping as much physical material out of the landfill as humanly possible.
Section 5. Towards a circular future. Closing the loop.
The entire point of mapping out this cradle-to-grave journey is so we can figure out how to fundamentally change it. We have to find a way to close the loop entirely, and the solution is moving toward what we call a circular tech economy. Achieving this means we've got to combine that rigorous, real-time tracking of our e-waste with brand-new, cleaner material sciences. For example, researchers over at Harvard are currently developing ways to use bacteria instead of those highly toxic chemicals to separate rare earth metals. A true circular economy means we have to fix both the end of the life cycle and the very beginning.
As ESG, environmental, social, and governance commitments become mandatory, and as regulatory scrutiny over data privacy heats up, this quote really nails the new standard: provable, real-time, item-level assurance for every data-bearing asset at scale. Having total accountability over our physical hardware, it's no longer just some nice-to-have, feel-good green initiative. It is a mandatory corporate control point. So I want to leave you with this final thought. Next time you log on and use one of these incredible generative AI tools to write code, whip up an image, or crunch some data, keep the physical biography of that compute power in the back of your mind. Ask yourself, are we building a truly sustainable digital intelligence, or are we just accelerating our way toward a smarter, more toxic landfill? Thank you so much for joining me for this explainer. Until next time, keep questioning the systems that power our world.